Time passes. For everyone, everywhere, at the same rate. Yet imagine you board a spaceship traveling near the speed of light while your twin stays on Earth. You journey to a distant star and return. From Earth's perspective, decades have passed. Your twin has aged, their hair has greyed, the world has changed. But when you step off the ship, you've barely aged at all. A few years, maybe less. How is this possible? If time passes for everyone at the same rate, how can one twin age decades while the other ages only years? And here's the deeper question. Isn't motion relative, from your perspective on the ship? Wasn't Earth moving away and back? Shouldn't your twin be the younger one? Welcome to Sleep Knowledge. If you find these gentle explorations helpful, subscribe so they're here whenever sleep feels distant. Tonight, we're going to explore the twin paradox, not as a contradiction, but as a window into how space-time actually works. And along the way, we'll discover why time's flexibility is the universe's way of keeping causality intact and reality coherent, and why that asymmetry isn't a paradox, it's what makes the universe consistent. Let's begin with something that feels obvious. Time ticks forward, second by second, the same for everyone watching the same clock. You and your twin celebrate birthdays on the same day, year after year. That's how time works, universal, steady, reliable, or so it seems. For most of human history, time was absolute. Newton described it as flowing uniformly, independent of anything external, a cosmic metronome ticking at the same rate everywhere in the universe. Time on Earth, time on distant stars, time in empty space, all synchronized perfectly. This made intuitive sense. Your experience confirms it every day. Clocks on walls tick in rhythm. Your heartbeat maintains its pace. Seasons cycle with regularity. Time feels universal because at human scales and human speeds, it essentially is. But there's a hidden assumption in that universality. The assumption that time is separate from space, that time flows independently, unaffected by motion or gravity or the structure of the universe itself. This assumption held for centuries. It worked beautifully for predicting planetary orbits, designing clocks, organizing daily life. No experiment suggested otherwise. Until the late 1800s. That's when physicists began seriously studying light. And light, it turned out, behaved strangely. Light has a speed 299,792,458 meters per second. Fast, but finite. And here's what made it strange. That speed appeared to be the same for every observer, regardless of their own motion. Shine a flashlight while standing still. Light leaves at 299,792,458 meters per second. Shine a flashlight while running forward. Light still leaves at exactly 299,792,458 meters per second. This shouldn't work. In everyday experience, speeds add. If you throw a ball forward from a moving train, the ball's speed relative to the ground is the train's speed plus your throwing speed. That's how motion combines. But light doesn't do this. Its speed is constant, always, no matter who's measuring or how they're moving. This created a problem. If light's speed is truly the same for all observers, something else has to give. Something has to be flexible to accommodate that constancy. In 1905, Albert Einstein proposed the radical answer. Time and space themselves are what give. They're not absolute, they're not independent. They bend, stretch, and adjust to keep light's speed constant for everyone. This was special relativity, and one of its immediate consequences was time dilation, the slowing of time for objects in motion. Time dilation means this. If you're moving relative to someone else, time passes more slowly for you than for them. Not subjectively, not as a perception or illusion. Actually. Your clock ticks slower, Your biological processes run slower. You age slower. The effect is real, measurable, and tiny at everyday speeds. Walking, driving, even flying in a jet produces time dilation, so small it's imperceptible. But approach the speed of light, and the effect becomes dramatic. At 90% of light speed, time passes about half as fast for you as for someone stationary. At 99% of light speed, time passes about 1/7 as fast. At 99.9%, about 1/22 as fast. The closer you get to light speed, the more extreme the dilation becomes. And this is where the twin paradox emerges. Imagine two twins, identical in age. One stays on Earth, the other boards a spacecraft capable of reaching speeds near light. The traveling twin accelerates to, say, 90% of light speed. They travel to a star 10 light years away. Then they turn around and come back at the same speed. From Earth's perspective, the journey takes a specific amount of time. Light travels at a fixed speed, so the round trip to a star 10 light years away and back 20 light years total takes just over 22 years, at 90% of light speed. The Earth twin ages 22 years. They watch seasons pass, birthdays come and go, the world change around them. That the traveling twin experiences something different. Because they're moving at 90% of light speed, time dilation applies. Time passes more slowly for them. Not from their own perspective they feel normal. Their heartbeat feels regular. Their clock seems to tick normally. But relative to Earth, their time is dilated. By the time they return, they've aged only about 10 years, half the time that passed on Earth. Same journey, same starting age, but one twin is now 22 years older, the other only 10 years older. This is the twin paradox. Not the age difference itself, that's just time dilation, a confirmed prediction of relativity. The paradox is this. Motion is supposed to be relative. From the travelling twins' perspective, aren't they stationary while Earth moves away and returns? Shouldn't the Earth twin be the one who ages less? Both twins see the other moving. So why isn't the time dilation symmetric? Why does one twin actually age more than the other? This is where intuition strains. If motion is relative, there should be no preferred reference frame, no objective answer to who's really moving. Both perspectives should be equally valid. Yet when they reunite, there's an objective, measurable difference in their ages. One has aged more, the other less. How can both perspectives be valid if the outcome is asymmetric? This question troubled physicists when Einstein first proposed relativity. Some saw it as a fatal flaw in the theory, a contradiction that proved relativity couldn't be right. But the paradox isn't a contradiction. It's a misunderstanding of what relativity actually says. The key is in the details, in the assumptions hidden beneath the apparent symmetry. And the first assumption to examine is this. Are the two twins' situations truly symmetric? At first glance, yes, one twin moves away, then returns. From the Earth twin's view, the travelling twin is moving. From the travelling twin's view, Earth is moving. But look closer. The Earth twin remains at rest in a single reference frame the entire time. They don't accelerate, they don't change direction, they experience no forces pushing them into their seat. The travelling twin, however, must accelerate. 3 times, actually. First, they accelerate from rest to reach 90% of light speed. Second, they decelerate, stop, and accelerate in the opposite direction to turn around at the distant star. Third, they decelerate again to stop at Earth. Those accelerations are real, physical, felt as forces pressing the traveller into their seat, and they break the symmetry. The Earth twin experiences no such forces. They remain in an inertial reference frame, a frame where Newton's first law holds, where objects at rest stay at rest unless acted upon. The traveling twin does not. They switch reference frames. They feel forces. Their path through spacetime is fundamentally different. This asymmetry is the key to resolving the paradox. But understanding why requires looking more carefully at what acceleration does to time, to space, and to the very notion of now. Let's build this slowly. First, imagine you're the Earth twin. You watch your sibling's spacecraft accelerate away. As it picks up speed, you notice something strange. Their clock appears to run slower. This is time dilation in action. From your frame of reference, their time genuinely passes more slowly. If you could watch them move, they'd appear to move in slow motion. Their heartbeat would slow, their aging would slow. This isn't an optical illusion. It's not about the time it takes light to reach you. Even accounting for light travel time, their clock is actually running slower than yours. You continue watching as they travel to the distant star, turn around, and return. Throughout the entire journey, you see their clock running slow. By the time they arrive back at Earth, your clock shows 22 years have passed. Theirs shows only 10. From your perspective, the explanation is straightforward. They were moving, so time dilation slowed their clock. You were stationary, so your clock ran normally. Simple, consistent, no paradox. Now imagine you're the traveling twin. You board the spacecraft, the engines ignite. You feel acceleration press you into your seat as the ship picks up speed. Looking back at Earth, you see it receding, and you notice something. Earth's clocks appear to run slower. This is also time dilation. From your reference frame, Earth is moving away from you, so from your perspective, time on Earth should be dilated. You continue traveling. Earth shrinks behind you. The distant star grows ahead. Earth's clocks keep ticking slowly. Then you reach the star. You fire your engines to turn around. You feel acceleration again, strong forces pressing you into your seat as your velocity reverses. And here's where something crucial happens. During that turnaround, your reference frame changes. You switch from moving away from Earth to moving toward Earth. And with that switch, something strange occurs with your notion of simultaneity. Simultaneity. The set of events you consider to be happening now is not absolute in relativity. It depends on your reference frame. When you were moving away from Earth, your now was one set of events on Earth. When you turn around and start moving toward Earth, your now suddenly includes a different, much later set of events on Earth. From your perspective, Earth's clock doesn't just tick slowly during your turnaround, it appears to jump forward. Not because time on Earth actually speeds up, but because what you consider simultaneous with your present moment shifts dramatically when you change velocity. This shift accounts for the missing time. On the outbound journey, you see Earth's clock running slow. On the inbound journey, you also see Earth's clock running slow. But during the turnaround, when you're accelerating and changing reference frames, Earth's clock effectively jumps ahead. When you account for all three phases, the total aging on Earth ends up being more than your own aging. The asymmetry comes from your acceleration, from your change in reference frames, from the fact that you didn't remain in a single inertial frame throughout the journey. And that asymmetry is real, physical, and measurable. This is starting to resolve the paradox, but it raises deeper questions. Why does acceleration matter? What is it about changing reference frames that creates this asymmetry? And how do we reconcile the traveling twin's perspective, where Earth's clock runs slow most of the time, with the final result, where Earth's clock has advanced more? The answers lie in the geometry of spacetime. Not the geometry of space alone, but of space and time woven together into a single four-dimensional fabric. In everyday thinking, space and time are separate. You move through space. Time flows independently. 3 dimensions of space, 1 dimension of time, forever distinct. But relativity shows they're unified. Space and time form a single entity called spacetime. Events don't just have locations in space, they have locations in space-time, specified by both where and when they occur. Your path through life isn't just a path through space. It's a path through space-time, a world line that tracks both your position and your moment in time. And here's the crucial insight. Different paths through space-time accumulate different amounts of proper time. Proper time is the time you actually experience, the time measured by a clock you carry with you, the time your body ages. In space-time, the proper time along a path depends on the geometry of that path. And remarkably, the longest proper time, the most aging, comes from the straightest path through space-time. This is counterintuitive. In ordinary space, the shortest distance between 2 points is a straight line, but in space-time, the longest proper time between two events is the straightest world line. The Earth twins' world line is straight. They remain in a single inertial frame, experiencing no acceleration. Their path through space-time is a straight line from the starting event to the reunion event. The traveling twins' world line is not straight. They accelerate, change direction, accelerate again. Their path through space-time bends. It curves away from the straight line, then curves back. And that curved path accumulates less proper time. This is why the traveling twin ages less, not because of some mysterious force acting on them, but because the geometry of space-time assigns different proper times to different paths. The straight path ages more, the curved path ages less. It's built into the structure of space-time itself. To visualize this, imagine a space-time diagram, a graph where the horizontal axis represents space and the vertical axis represents time. The Earth twins' world line is a vertical line, staying at the same position in space while advancing through time. The traveling twins' world line angles away, moving through space as they move through time, then angles back, forming a V shape. Both world lines start at the same event, the departure. Both end at the same event, the reunion. But the proper time along each world line is different. In space-time geometry, proper time is calculated using the metric, a mathematical rule that describes how to measure intervals in space-time. The metric for flat space-time, called the Minkowski metric, has a special property. Time and space contribute with opposite signs. When you're stationary in space and moving only through time, you accumulate proper time at the maximum rate. When you're moving through space, your rate of proper time accumulation decreases. The faster you move through space, the slower you move through time. This is time dilation, expressed geometrically. The Earth twin, stationary in space, accumulates proper time at the maximum rate. The traveling twin, moving through space at high speed, accumulates proper time at a slower rate. Integrate along both world lines, and the Earth twin's proper time is greater. The paradox resolves, not through hand-waving, but through rigorous geometry. But there's still the question of acceleration. Why does the traveling twin's acceleration matter? Special relativity is supposed to deal with inertial frames moving at constant velocity. Acceleration brings in non-inertial frames, which is the domain of general relativity. Is general relativity needed to resolve the twin paradox? Not quite. Special relativity can handle the paradox perfectly well, as long as you're careful. The key is that special relativity applies in inertial frames. The Earth twin is in an inertial frame the whole time, so their perspective is straightforward. The traveling twin is in an inertial frame during the outbound journey, a different inertial frame during the inbound journey, and neither inertial frame during the turnaround. You can analyze each inertial segment separately using special relativity. During the outbound journey, calculate proper time. During the inbound journey, calculate proper time. Add them up. The acceleration phase is brief, nearly instantaneous in idealized versions of the problem. During that brief moment, special relativity doesn't directly apply to the traveling twin's frame, but it doesn't need to. The proper time during a short acceleration is negligible. What matters is that the acceleration changes which events on Earth are simultaneous with the traveler's present moment. Before the turnaround, events on Earth that are now for the traveler are early in the Earth twins timeline. After the turnaround, events on Earth that are now for the traveler have jumped ahead. This shift in simultaneity accounts for the asymmetry. The Earth twins now is unambiguous. They never change frames. The traveling twins now is frame dependent and jumps during acceleration. So while general relativity provides a more complete picture, especially if you want to analyze the turnaround in detail, it's not strictly necessary. Special relativity, carefully applied, resolves the paradox. Still, general relativity offers a beautiful perspective. In general relativity, gravity and acceleration are equivalent. This is the equivalence principle, one of Einstein's key insights. When you're in an accelerating spaceship, you feel a force pressing you into your seat. You can't tell, from inside the ship, whether that force is due to acceleration or to gravity. General relativity treats them the same. Acceleration is indistinguishable from being in a gravitational field, and gravity affects time. In a gravitational field, time passes more slowly deeper in the field than higher up. This is gravitational time dilation. On Earth's surface, time passes slightly slower than in orbit. GPS satellites experience this. They're higher in Earth's gravitational field, so time runs faster for them. Similarly, during the traveling twins' acceleration, they're effectively in a gravitational field, and from their accelerated perspective, Earth is higher in that field, so time on Earth runs faster. This is another way to understand the time jump during turnaround. The traveling twin, accelerating, experiences a pseudo-gravitational field that causes Earth's time to run fast. Integrate that effect over the turnaround period, and it accounts for the missing years. So whether you analyze it with special relativity and changing simultaneity, or with general relativity and pseudo-gravitational time dilation, the result is the same. The traveling twin ages less, the Earth twin ages more. The paradox resolves. At this point you might wonder, is this just theoretical, or has it actually been tested? The answer is extensively tested, with remarkable precision, in multiple ways. And every test confirms the prediction. The most direct test of the twin paradox came in 1971, in an experiment designed by physicists Joseph Hafele and Richard Keating. They took atomic clocks, extremely precise timekeepers, and flew them around the world on commercial airplanes. One set of clocks flew eastward, in the direction of Earth's rotation. Another set flew westward, against Earth's rotation. A third set stayed on the ground as a reference. When the clocks returned, they compared the elapsed time. The predictions from relativity were clear. The flying clocks should show less time elapsed than the ground clocks due to their motion special relativistic time dilation. But they should also show more time elapsed than the ground clocks because they were at higher altitude, experiencing weaker gravity, general relativistic time dilation. The two effects partially offset each other, but not completely. The exact offset depends on the direction of flight. Eastward flights move with Earth's rotation, so their speed relative to Earth's center is higher, more time dilation from speed. Westward flights move against Earth's rotation, so their speed relative to Earth's center is lower, less time dilation from speed. Hafele and Keating calculated the predicted difference for each set of clocks, down to the nanosecond. Then they measured the actual difference. The results matched the predictions. Within experimental uncertainty, the clocks showed exactly the time difference relativity predicted. Eastward flying clocks lost about 59 nanoseconds compared to the ground clocks. Westward flying clocks gained about 273 nanoseconds. Different amounts of aging for clocks taking different paths through spacetime. The twin paradox, demonstrated with atomic clocks on airplanes. Since then, the effect has been measured with even greater precision. Modern atomic clocks are so accurate they can detect time dilation from differences in speed of just a few meters per second, from differences in altitude of just a few centimeters. In 2010, physicists at the National Institute of Standards and Technology used optical atomic clocks, clocks that use light frequencies to keep time to measure time dilation at walking speed. They put one clock on a platform. They raised another clock by just 33 centimeters, about 1 foot. The higher clock ticked faster, as predicted by general relativity. The difference was tiny, about 90 parts in a quintillion, but measurable. They also put one clock on a platform moving at just a few kilometers per hour slower than a bicycle. The moving clock ticked slower, as predicted by special relativity. These aren't exotic conditions. These are everyday speeds and everyday heights. Yet time dilation is real and measurable. The universe doesn't reserve relativity for spaceships traveling near light speed. It applies everywhere, all the time. You just need clocks precise enough to see it. Another powerful test comes from particle physics. Unstable particles, particles that decay into other particles after a short time, provide natural clocks. Their decay times are fixed by quantum mechanics. Muons are one example. A muon at rest decays in about 2.2 microseconds on average. Muons are created in Earth's upper atmosphere when cosmic rays collide with air molecules. These muons travel downward at speeds close to the speed of light, often 99.9% of light speed or faster. At those speeds, time dilation is dramatic. A muon traveling at 99.9% of light speed experiences time dilation by a factor of about 22. Its 2.2 microsecond lifespan, from our perspective, stretches to about 48 microseconds. In 2.2 microseconds, even at nearly light speed, a muon travels only about 660 meters. But in 48 microseconds, it can travel over 14 kilometers. The atmosphere is thicker than 660 meters. If muons didn't experience time dilation, almost none would reach the ground. They'd decay long before completing the journey. But we detect muons at sea level constantly, thousands per square meter per minute. Their survival proves time dilation. They age more slowly because they're moving fast. From their perspective, their lifespan is still 2.2 microseconds. But from our perspective, stretched by time dilation, they live long enough to reach the ground. This is the twin paradox playing out with particles. The fast-moving muons age less than if they'd been stationary. Particle accelerators provide even more dramatic examples. At CERN, the Large Hadron Collider accelerates protons to 99.9999991% of the speed of light. At that speed, time dilation is a factor of about 7,500. Protons don't decay, they're stable particles, but other particles created in collisions do, and their decay times stretch exactly as relativity predicts. Engineers designing particle accelerators must account for time dilation. Without it, the math doesn't work. The particles wouldn't behave as observed. Technology depends on relativity being correct, not approximately, exactly. The twin paradox isn't a thought experiment anymore. It's engineering reality. And then there's GPS. The global positioning system relies on satellites orbiting Earth at about 20,000 kilometers altitude, moving at roughly 14,000 kilometers per hour. GPS works by timing. Each satellite broadcasts a signal containing the time it was sent. Your GPS receiver compares the arrival time to the current time, calculates how long the signal took to arrive, and uses that to determine your distance from the satellite. With signals from multiple satellites, your receiver can triangulate your position. The system requires nanosecond precision. Light travels about 30 centimeters in a nanosecond, so even tiny timing errors translate to significant position errors. And relativity creates timing differences. The satellites are moving, so special relativity predicts their clocks should tick slower than ground clocks, by about 7 microseconds per day. But the satellites are also higher in Earth's gravitational field, so general relativity predicts their clocks should tick faster than ground clocks, by about 45 microseconds per day. The net effect: satellite clocks tick about 38 microseconds per day, faster than ground clocks. 38 microseconds doesn't sound like much, but it accumulates. Light travels 11 kilometers in 38 microseconds. If GPS didn't correct for relativity, position errors would grow by about 11 kilometers per day. After one day, your GPS would be off by 11 kilometers. After 1 week, 77 kilometers. The system would be useless. So GPS satellites have their clocks adjusted before launch. They're set to tick at a different rate than ground clocks, slightly slower, so that once in orbit, with relativistic effects applied, they sync with ground time. Every time you use GPS, you're relying on the twin paradox being true. Your phone corrects for time dilation. It accounts for the fact that clocks in motion age differently than stationary clocks. The twin paradox is in your pocket. So the effect is real, tested, applied in technology you use daily. But does that mean we fully understand it? That every question is answered? Not quite. There are deeper layers, subtleties that reveal even more about how time and space work together. And exploring those layers brings a kind of calm, the calm that comes from seeing how much structure underlies what seems strange. Let's return to the twin paradox with fresh eyes. We've established that the travelling twin ages less because they accelerate. Their path through space-time is curved, accumulating less proper time than the straight path of the Earth twin. But what if we complicate the scenario? What if, instead of one travelling twin, there are 3 participants? Twin A stays on Earth. Twin B travels outbound at high speed. Twin C travels inbound at high speed, passing Twin B at the turnaround point. Twin B and Twin C are both always moving at constant velocity, no acceleration. They just happen to pass each other at the distant star. When they pass, they synchronize clocks. Twin C takes note of Twin B's clock reading and carries that information back to Earth. Does this eliminate the acceleration? Does it restore symmetry? No. The asymmetry remains. Twin B and Twin C are each in inertial frames the whole time, but they're in different inertial frames. Twin B's frame says one set of events on Earth is simultaneous with the passing event. Twin C's frame says a different, later set of events on Earth is simultaneous with the passing event. Even though there's no acceleration, there's still a change in reference frame from Twin B's frame to Twin C's frame. And that change in reference frame still creates a shift in simultaneity. Earth's clock still jumps forward in the transition from B's perspective to C's perspective. The result is the same. When Twin C returns to Earth, they find Twin A has aged more. The acceleration isn't necessary for the asymmetry. What's necessary is the change in reference frame. Acceleration just happens to be the usual way to change reference frames. But even without it, if you switch from one inertial observer to another, the asymmetry emerges. This highlights something profound. The twin paradox isn't about acceleration per se. It's about the geometry of paths through space-time. One twin follows a single straight world line. The other, whether by accelerating or by handing off to another observer, follows a bent or segmented path. The straight path maximizes proper time. The bent path doesn't. That's the essence of it. And this reveals something comforting. The universe has rules, deep, geometric rules. Those rules don't change based on how you feel about them. They don't shift based on perspective in a way that creates contradiction. Different observers see different things, yes, but those different observations fit together coherently. Each twin's measurements are valid in their own reference frame, and when you account for the geometry for how reference frames relate to each other, everything aligns. There's no paradox, only structure. And that structure extends beyond the twin paradox. Consider what relativity implies about the nature of now. In everyday experience, now seems universal. Right now, at this moment, events are happening all over the world. Your friend is reading a book in Paris right now. A whale is diving in the Pacific right now. A star is burning in a distant galaxy right now. But relativity says, now is frame-dependent. What you consider simultaneous with your present moment depends on your velocity. If you're stationary, one set of events is happening now. If you're moving, a slightly different set of events is happening now. The difference is tiny at human speeds. Walking shifts your simultaneity by nanoseconds over cosmic distances. But at speeds close to light, the shift becomes enormous. An observer moving at 99% of light speed toward a distant galaxy has a now that includes events in that galaxy's far future. An observer moving away from that galaxy at 99% of light speed has a now that includes events in that galaxy's distant past. Same galaxy, same moment for the observers, but completely different sets of events are simultaneous. This doesn't mean the future already exists or the past still exists in some objective sense. It means simultaneity is relative. And this relativity of simultaneity is what allows the twin paradox to resolve without contradiction. The traveling twins now shifts when they change velocity. The Earth twins now doesn't shift, they never change frames. Both are measuring real things. Both are correct within their frames, but their frames are different, so their measurements differ. And when they reunite, when they're finally in the same frame again, the accumulated proper time along their different paths reveals the asymmetry. There's another way to visualize this using Doppler shifts. Imagine the Earth twin sends a light signal to the traveling twin once per year. A birthday message, perhaps. From Earth's perspective, 22 signals are sent during the traveling twin's journey, one per year for 22 years. But the traveling twin doesn't receive them evenly spaced. On the outbound journey, the traveling twin is moving away from Earth. The signals are Doppler shifted, stretched out in time. If the twin is moving at 90% of light speed, the signals arrive about once every 4.4 years instead of once per year. The outbound journey takes 10 years from the traveler's perspective, so they receive about 2 to 3 signals during that time. Then they turn around and head back. Now they're moving toward Earth. The signals are Doppler shifted the other way, compressed in time. The signals arrive much faster, about every 0.23 years, roughly every 3 months. The inbound journey also takes 10 years from the traveler's perspective. During those 10 years, they receive the remaining signals, about 19 or 20 of them. Add it up, 2 to 3 signals on the way out, 19 to 20 on the way back, totaling 22 signals. The same 22 signals Earth sent. The traveling twin receives all 22 signals, but they're bunched asymmetrically. Most arrive during the return journey, when the Doppler shift works in the opposite direction. This accounts for the time difference. From the traveler's perspective, Earth's clock was ticking slowly. During most of the journey, signals arrived, stretched out. But during the turnaround and return, Earth's clock appeared to tick much faster. Signals arrived compressed. The net result, when all signals are counted, Earth's clock has advanced 22 years, while the traveler's has advanced only 10. No paradox, just asymmetric Doppler shifts that match the asymmetric motion. Now consider the reverse. The traveling twin also sends signals back to Earth, one per year from their perspective. They age 10 years during the journey, so they send 10 signals total. Earth receives these signals over the course of 22 years, but not evenly spaced. During the outbound phase, Earth is receding from the traveler's perspective, but from Earth's perspective, the traveler is receding. The signals are Doppler shifted stretched. Earth receives them spaced out. Earth receives about 2 signals during the first 11 years, the time it takes for the traveler to reach the distant star. Then the traveler turns around. Signals sent during the return journey are compressed by Doppler shift. Earth receives them much faster. Over the next 11 years, as the traveler returns, Earth receives the remaining 8 signals. Total, 10 signals, matching the 10 years the traveler aged. From Earth's perspective, the traveler's clock was ticking slowly. Most of the time, signals arrived, stretched out for 11 years, then compressed for 11 years, but the total count is only 10. This matches perfectly with time dilation. The traveler aged 10 years, while Earth aged 22. The Doppler perspective is satisfying because it's purely observational. You don't need to invoke reference frames or space-time geometry. You just count signals. And the count is consistent. Both twins agree on how many signals were sent and received. The asymmetry is in the timing, not the total count. This asymmetry reflects the asymmetry in their motion. The Earth twin never changes velocity. The traveling twin does. And that change, whether you call it acceleration, a switch in reference frames, or a bend in the world line, is what breaks the symmetry and resolves the paradox. But let's push further. What if both twins accelerate? Imagine both twins start on Earth. Both board spaceships. Both accelerate to high speed. One heads toward a distant star. The other heads in the opposite direction. They travel for a while, then both turn around and return to Earth. Their journeys are symmetric. Same speeds, same distances, same accelerations. When they reunite, how much has each aged? The answer, the same amount. Both followed paths through space-time with the same geometry. Both experienced the same time dilation. Both aged identically. There's no paradox here because there's no asymmetry. The twin paradox only arises when one twin remains inertial and the other doesn't. If neither remains inertial, or if both follow identical non-inertial paths, their aging is symmetric. This reinforces the key point. The paradox comes from comparing an inertial path with a non-inertial path. The inertial path straight through space-time accumulates more proper time. The non-inertial path bent or curved accumulates less. Now imagine a more extreme scenario. One twin stays on Earth. The other boards a spaceship and accelerates continuously at 1g, the same acceleration you feel from gravity on Earth's surface. Accelerating at 1g feels comfortable. It mimics normal gravity. The traveler can walk around, live normally, experience no discomfort. The ship accelerates for 1 year from the traveler's perspective, then it decelerates at 1g for another year, comes to a stop, reverses, and accelerates back toward Earth for 1 year, then decelerates for 1 final year. Total journey time from the traveler's perspective, 4 years. But from Earth's perspective, far more time has passed. The faster the traveler goes, the more time dilation applies, and continuous acceleration at 1g gets you moving very fast. After 1 year of continuous 1g acceleration, the traveler is moving at about 77% of light speed. After 2 years, over 97%. Time dilation at those speeds is substantial. By the time the traveler completes the 4-year round trip from their perspective, Earth has aged significantly more. The exact amount depends on the distance traveled, but for a journey to a star about 12 light-years away, Earth would age roughly 30 years. The traveler experiences 4 years. Earth experiences 30. The traveler returns to an Earth decades older. Friends have aged. The world has changed. This is the twin paradox taken to its logical extreme, and it's not science fiction. It's what relativity predicts, and relativity has been confirmed in every test. Of course, No current technology can sustain 1g acceleration for years. Our fastest spacecraft reach tiny fractions of light speed and can't maintain acceleration for long. But the physics is clear. If you could build such a ship, this is what would happen. The traveler would age less. Earth would age more. And this creates fascinating possibilities for deep space exploration. Imagine a journey to a star 100 light-years away. At ordinary speeds, it would take far longer than a human lifetime. But with constant 1g acceleration, the traveler could reach the star in about 7 years, from their perspective. They'd accelerate for half the journey, decelerate for the other half, arrive at the star without having aged much at all. Of course, Earth would have aged over 200 years. Everyone the traveler knew would be long dead. Civilization would have changed unrecognizably. The traveler becomes unstuck from their own time. They age slowly while the universe ages normally. This is time travel, in a sense. Forward time travel. You can journey into Earth's future by traveling fast and returning. You can't go back. Relativity doesn't allow backward time travel, at least not without exotic phenomena like wormholes or closed time-like curves, which may not be physically possible. But forward time travel is not only possible, it's inevitable for anything that moves. You're time traveling right now, very slightly, by moving through space. Walk across the room, and you've aged microseconds less than if you'd stayed still. The effect is negligible, but it's real. This brings up an interesting question. What's the maximum time dilation you could achieve? In principle, there's no limit. The closer you get to light speed, the more extreme time dilation becomes. At 99.999999% of light speed, time dilation is a factor of over 70,000. 1 year for you equals 70,000 years for a stationary observer. At even closer to light speed, the factor grows without bound. But there's a practical limit: energy. Accelerating to high speeds requires energy, and the closer you get to light speed, the more energy is required. In relativity, an object's energy increases with velocity. At low speeds, kinetic energy is the familiar 1/2 mv squared, but at high speeds, the formula changes. As you approach light speed, your energy approaches infinity. You'd need infinite energy to actually reach light speed. This is why nothing with mass can travel at light speed. It's not just difficult, it's impossible. Light itself travels at light speed because photons have no mass. For them, it's the only speed available. But anything with mass is forever limited to speeds below light speed. So while time dilation can be arbitrarily large in principle, achieving it requires energy that quickly becomes impractical. Still, even modest time dilation opens remarkable possibilities. There's also the question of perception. What does it feel like to experience time dilation? The answer? Perfectly normal. From your own perspective, time always passes at the same rate, 1 second per second. Your heartbeat doesn't feel slower. Your thoughts don't feel sluggish. Clocks you carry tick normally. It's only relative to someone in a different frame that your time appears dilated. This is a crucial point. Time dilation is not something you feel. It's something others observe about you. You never experience your own time as anything other than normal. Which makes sense. Time is what clocks measure, and clocks you carry are moving with you. They're in your frame. They tick in sync with your heartbeat, your neurons, your biological processes. Everything in your frame ages together, so from within that frame, everything feels normal. It's only when you compare your frame to another, when the traveling twin reunites with the Earth twin, that the difference becomes apparent. This raises philosophical questions. If you never feel time dilation, is it real? The answer is yes, unambiguously. Reality isn't limited to what you feel. Your feelings reflect your local experience, but the universe is larger than any single frame. When the twins reunite, the difference in their ages is objective, measurable, undeniable. One has more grey hair, more wrinkles, more years of memory. The other has aged less. This isn't a difference in perception. It's a difference in proper time, actually elapsed along different world lines. Both experiences are real, but they're different, and the universe allows both to be true simultaneously, because time is not absolute. This flexibility might seem unsettling at first. The idea that time isn't universal, that different observers experience different amounts of it, challenges deep intuitions. But there's comfort in recognizing that this flexibility is lawful. It's not chaos, it's geometry. Space-time has a structure, and different paths through that structure accumulate different amounts of proper time. The rules are precise, the math is consistent, the predictions match observations. This is not a universe where anything goes. It's a universe with deep, reliable laws. And those laws permit twins to age differently, not as a glitch or contradiction, but as a natural consequence of space-time's geometry. There's also a connection to entropy and the arrow of time. Time dilation affects the rate at which time passes, but it doesn't reverse time's direction. Entropy disorder still increases for both twins. Eggs still break, heat still flows from hot to cold, processes still move forward. Time dilation changes the rate, not the arrow. The travelling twin ages slower, but they still age forward. Their memories still accumulate. Their body still moves from young to old, not the reverse. This is important because it means time dilation doesn't create causal loops or paradoxes involving causality. Cause still precedes effect in every frame. The order of causally connected events, events where one can influence the other, is preserved across all frames. You can't use time dilation to send a message into your own past. Events outside each other's light cones can have their order reversed depending on the observer, but those events can't influence each other anyway. Events inside each other's light cones where influence is possible maintain their causal order. This is built into the structure of space-time. The metric ensures it. So relativity protects causality even as it makes time flexible. Consider what this means for the universe at large. Every particle, every object, every observer is following a world line through space-time. Each world line accumulates proper time at its own rate, depending on its path. Objects at rest accumulate proper time fastest. Objects in motion accumulate it slower. Objects in strong gravitational fields accumulate it slower still. Yet, all these world lines weave together coherently. When world lines intersect, when objects meet, they can compare their clocks, and they always find consistency. The travelling twin ages less, the stationary twin ages more. GPS satellites tick faster than ground clocks. Muons live longer when moving. Every measurement confirms the geometry. Every observation fits the pattern. The universe doesn't contradict itself. It just operates according to rules that are more subtle than everyday intuition suggests. And this subtlety extends to how we think about existence itself. In Newton's universe, there was a universal now, a single moment in time that applied everywhere. You could ask, what is happening right now on Mars? And there was an objective answer. In Einstein's universe, that question doesn't have a single answer. What counts as now on Mars depends on your velocity. For someone at rest relative to Mars, now on Mars is one set of events. For someone moving toward Mars, now on Mars is a slightly different, later set of events. For someone moving away from Mars, now on Mars is a slightly different, earlier set of events. There's no single objective now that spans the universe. Simultaneity is relative. This doesn't mean Mars doesn't exist when you're not observing it. It means the concept of existing at the same moment is frame-dependent. Events exist. They happen at specific locations in spacetime, but which events you call simultaneous with your present moment depends on your motion. This is deeply strange, but it's how the universe works. And once again, it's not arbitrary, it's geometric. It follows from the structure of spacetime and the constancy of light speed. Let's bring this back to the twin paradox one more time. The paradox asks, if motion is relative, why isn't time dilation symmetric? The answer, we've seen, is that motion is relative, but acceleration is not. Or more precisely, inertial motion is relative, but changes in inertial motion acceleration are absolute. You can tell, without looking outside, whether you're accelerating. You feel forces. Objects inside your spaceship get pushed around. But you can't tell, without looking outside, whether you're moving at constant velocity. Everything inside your spaceship behaves normally. This asymmetry between inertial and non-inertial motion is fundamental to relativity. And it's what resolves the twin paradox. The Earth twin remains inertial. No forces, no acceleration. A straight world line through spacetime. The traveling twin accelerates, feels forces, changes velocity. A curved world line through spacetime. The asymmetry in their experiences reflects the asymmetry in their paths. And spacetime's geometry assigns different proper times to those different paths. It's elegant, it's consistent, it's testable, and it's profoundly strange. Strange, but not threatening. Because the strangeness comes with structure, with rules, with predictability. You can calculate, before the journey, exactly how much each twin will age. You can predict the outcome based on the speeds, the distances, the accelerations. And when you perform the experiment, whether with atomic clocks on airplanes, muons in the atmosphere, or satellites in orbit, the prediction holds. The universe behaves exactly as the equations say it should. This reliability is comforting. It means the universe isn't arbitrary. It's not chaotic. It follows laws. Those laws might be counterintuitive. They might violate everyday assumptions about time and space. But they're laws nonetheless, consistent, dependable, knowable. And there's something calming in that knowledge. The twin paradox isn't a trick or a puzzle designed to confuse. It's a window into how the universe actually works. Time is flexible. Motion affects aging. Different paths through space-time accumulate different amounts of proper time. These aren't glitches in reality, they're features of space-time's geometry. And that geometry is stable. It doesn't change based on your mood or your beliefs. It simply is. You can trust it. Even when it surprises you. Even when it defies intuition. You can trust that the equations work, that the predictions hold, that the universe is coherent. This coherence extends all the way down. From the twin paradox to time dilation, to the constancy of light speed, from special relativity to general relativity, to the unification of space and time. Each piece fits with the others. Each prediction aligns with observation. There are no loose ends, no contradictions. Just a universe operating according to principles that are strange at first, but ultimately more elegant than the familiar Newtonian framework. A universe where time bends, space curves and twins can age differently. Yet a universe that remains, at its core, lawful and knowable. And perhaps that's the deepest lesson of the twin paradox. Not that time is strange, but that strangeness and reliability can coexist. That the universe can behave in ways that defy everyday intuition without becoming incomprehensible. That mystery and structure are not opposites but companions. The twin paradox remains mysterious even after you understand it. You can follow the math, you can trace the world lines, you can calculate the proper times, but it still feels surprising that time can be so flexible. And that surprise is appropriate. It's a sign you're grasping something genuinely new. Intuition, built from everyday experience, expects time to be universal. Relativity reveals that it's not. And adjusting to that revelation takes time. But the adjustment is possible, and the view from the other side where relativity seems natural is worth the effort. Because once you accept that time is relative, other pieces fall into place. You understand why nothing can travel faster than light, because approaching light speed requires infinite energy, and because faster than light travel would allow backward time travel, creating causal paradoxes. You understand why E equals mc squared, because energy and mass are related through the geometry of spacetime, and c is the conversion factor. You understand why gravity bends light, because gravity curves spacetime, and light follows the straightest possible path through that curved geometry. You understand why black holes have event horizons, because extreme curvature of spacetime creates regions where all paths lead inward, where even light can't escape. The twin paradox is one thread, but pulling on it reveals the entire tapestry of relativity, and that tapestry is beautiful. Strange, intricate, counterintuitive at times, but coherent, elegant, true. Let's explore some of the deeper implications of what the twin paradox reveals. One of the most striking aspects is how it connects to the nature of spacetime itself. Before relativity, space was space and time was time, separate, independent, 3 dimensions of space, 1 dimension of time. Relativity unified them into spacetime, a single 4-dimensional continuum. This unification isn't just mathematical convenience, it's physically meaningful. Space and time transform into each other depending on your velocity. What one observer measures as a distance in space, another observer measures as a combination of space and time. What one observer considers simultaneous events separated in space, another considers non-simultaneous events separated in both space and time. This mixing of space and time is called a Lorentz transformation. And it's not just a change in coordinates or perspective, it's a physical reality. The traveling twin literally experiences less time because their path through spacetime has a different geometry than the Earth twin's path. The geometry is real, the proper time is real, the aging difference is real. Spacetime is not just a mathematical abstraction, it's the arena in which physics happens. This has profound implications for causality. In a universe with absolute time, cause and effect are straightforward. If event A happens before event B in absolute time, then A can potentially cause B. But in relativity, with no absolute time, how do we preserve causality? The answer lies in the light cone structure of spacetime. Every event in spacetime has a past light cone, the set of all events that could have influenced it, and a future light cone, the set of all events it could influence. These light cones are defined by the paths light could travel to or from the event. If event A is in event B's past light cone, then A is unambiguously before B in time for all observers. A could have caused B. If event A is in event B's future light cone, then A is unambiguously after B for all observers. B could have caused A, but A couldn't have caused B. If event A is outside event B's light cone too far away to be connected by a light signal, then the order of A and B is frame-dependent. Some observers see A happening first, others see B happening first. But that's okay, because A and B can't influence each other anyway. They're space-like, separated too far apart in space and too close in time for any signal to connect them. So causality is preserved. Events that can influence each other have a definite order. Events that can't influence each other are allowed to have ambiguous order. The light cone structure ensures that relativity doesn't create causal paradoxes. And this structure is intimately connected to the constancy of light speed. Light speed is the maximum speed for any influence. It's the speed at which causality propagates. If something could travel faster than light, it could connect events outside each other's light cones. It could create closed causal loops effects preceding their causes. But nothing with mass can reach light speed, let alone exceed it. So causality is safe. The universe maintains its coherence. And the twin paradox fits perfectly within this structure. The twins' reunion is in both twins' futures from the moment they separate. There's no causal ambiguity. Both paths lead to the same event, just with different proper times elapsed. Another deep implication involves the equivalence principle. Einstein's equivalence principle states that acceleration is indistinguishable from gravity. If you're in a closed room accelerating through space at 1g, you feel exactly the same as if you were stationary on Earth's surface in 1g gravity. You can't tell the difference from inside the room. This equivalence is not approximate, it's exact, at least locally. And it connects the twin paradox to gravitational time dilation. We've discussed how motion causes time dilation. Gravity does too. The deeper you are in a gravitational field, the slower time passes. On Earth's surface, time passes slightly slower than in orbit. The difference is small, about 45 microseconds per day for GPS satellites, but measurable. Near a black hole, gravitational time dilation becomes extreme. Close to the event horizon, time nearly stops from the perspective of a distant observer. An observer falling into a black hole experiences time normally from their own perspective, but to someone far away, the infalling observer appears to slow down, redden, and freeze just outside the horizon. This isn't an optical illusion, it's gravitational time dilation taken to its limit. And it's connected to the twin paradox through the equivalence principle. During the traveling twins' acceleration, they're in a non-inertial frame. From their perspective, a pseudo-gravitational field appears. Earth, from the accelerating twins' perspective, is higher in that pseudo-gravitational field, and time runs faster higher in a gravitational field. So during acceleration, Earth's clock appears to run fast from the traveler's perspective. This is the same effect that causes the simultaneity shift we discussed earlier, just viewed through the lens of general relativity. Both perspectives, special relativity with changing reference frames and general relativity with pseudo-gravitational time dilation, give the same answer. The twins age differently. The traveling twin ages less. This consistency across different approaches is reassuring. It shows relativity is self-consistent. Now let's consider what happens in more complex scenarios. Suppose the traveling twin doesn't just go to one star and back. Suppose they visit multiple stars, turning around at each one. Earth twin stays put. Traveling twin visits star A, returns briefly to Earth, then visits star B, then star C, and so on. Each journey involves acceleration leaving Earth, turning at the star, returning to Earth, accelerating away again. Each journey accumulates time dilation. After 10 journeys, the traveling twin has aged much less than the Earth twin. The effect is cumulative. Each trip adds to the total aging difference. And each trip's contribution can be calculated precisely using the speeds and distances involved. The math is consistent. The geometry is consistent. The predictions match observations. Or consider a different scenario: circular motion. Suppose the traveling twin orbits Earth at high speed, not in a low orbit like the ISS, but in a much larger orbit, at a significant fraction of light speed. Circular motion involves constant acceleration. The twin is always turning, always changing direction, always experiencing centripetal acceleration. This acceleration breaks the symmetry, just as the turnaround in the classic twin paradox does. The orbiting twin ages less than the stationary Earth twin, and the amount can be calculated. It depends on the orbital speed and the duration of the orbit. GPS satellites experience this effect. They orbit Earth at high speed, so special relativistic time dilation slows their clocks. But they're also at high altitude, so gravitational time dilation speeds their clocks. The two effects partially cancel, but not completely. The net effect is that satellite clocks run faster than ground clocks. This is the twin paradox in a circular configuration, and it's been tested to extraordinary precision. GPS wouldn't work if the corrections weren't applied. Every navigation system on Earth depends on relativity being correct. There's also the question of perception during acceleration. We've said the travelling twin feels forces during acceleration, but what do they actually observe? During acceleration toward the distant star, the travelling twin sees the star ahead, Doppler shifted toward blue. Its light is compressed by the twin's motion toward it. They also see Earth behind them, Doppler shifted toward red. Its light is stretched by the twin's motion away from it. During the turnaround, the Doppler shifts reverse. Earth's light shifts from red toward blue. The star's light shifts from blue toward red. On the return journey, Earth is ahead and blue shifted. The star is behind and red shifted. These Doppler shifts are continuous and smooth. They're purely observational, what the travelling twin actually sees looking out the window. And they're consistent with time dilation. Blue shifted light arrives at a faster rate. Red shifted light arrives at a slower rate. When the travelling twin observes Earth's light blue shifted during the return journey, they're receiving more photons per second. Earth's clock appears to tick faster. When they observe Earth's light red shifted during the outbound journey, they receive fewer photons per second. Earth's clock appears to tick slower. Integrate over the entire journey, and the total number of photons received matches the total time elapsed on Earth. Everything fits together. Let's also think about energy. Accelerating the travelling twin to high speeds requires enormous energy. The faster you want to go, the more energy you need, and as you approach light speed, the energy requirement increases without bound. This isn't a technological limitation, it's fundamental. In relativity, an object's energy is given by E equals gamma mamc squared, where gamma is the Lorentz factor, the time dilation factor. At low speeds, gamma is approximately 1, and the formula reduces to E is approximately equal to mc squared plus 1/2 mv squared, the rest energy, plus kinetic energy. At high speeds, gamma grows. At 90% of light speed, gamma is approximately equal to 2.3. At 99%, gamma is approximately equal to 7. At 99.9%, gamma is approximately equal to 22. The energy increases proportionally. To accelerate a 1,000 kilogram spacecraft to 90% of light speed requires about 1.3 times its rest energy, roughly 10 to the power of 20 joules. That's comparable to the total energy output of the Sun over several seconds. To reach 99.9% of light speed requires about 22 times the rest energy, even more astronomical. Current technology is nowhere near capable of this. The fastest spacecraft ever built, the Parker Solar Probe, reaches about 0.06% of light speed. But the physics is clear. If you had the energy, you could accelerate to these speeds, and if you did, time dilation would occur exactly as predicted. The energy requirement isn't arbitrary. It's connected to the structure of spacetime. Accelerating an object means changing its path through spacetime, and the energy required reflects the curvature of that path. The more you want to curve your worldline, the faster you want to travel, the more energy you need. This brings us to another fascinating consequence, the so-called twin paradox resolution through radar ranging. Imagine both twins carry radar devices. They continuously send signals to each other and time how long it takes for the echoes to return. From Earth, the twin sends a radar pulse toward the spaceship. The pulse travels at light speed, reaches the ship, bounces back, and returns to Earth. The round-trip time tells Earth how far away the ship is. Similarly, the traveling twin sends pulses toward Earth and times the echoes. Throughout the journey, both twins continuously measure their separation using radar. And something interesting emerges. From Earth's perspective, the radar echoes show the ship moving away at a certain speed, turning around at a certain distance, and returning. From the ship's perspective, the radar echoes show Earth moving away, reaching a maximum distance, and returning. Both perspectives are valid. Both give consistent measurements of distances and speeds. But when you account for the Doppler shifts of the radar signals, how the signals are time-dilated depending on relative motion, the timing works out perfectly. Earth's radar confirms the ship was gone for 22 years. The ship's radar confirms it was only 10 years. The radar measurements are frame-dependent, but they're consistent. Both twins can use radar to map out the entire journey, and both maps are correct within their respective frames. And when the twins reunite and compare notes, the maps align. The aging difference is confirmed. Another way to think about the twin paradox is through the concept of invariant intervals. In spacetime, there's a quantity called the spacetime interval, which is a measure of the distance between two events. But unlike distance in ordinary space, the spacetime interval combines space and time with a minus sign. For two events separated by a distance deltax and a time deltat, the interval is deltas squared equals c squared deltat squared deltax squared. This interval is invariant. All observers agree on its value, regardless of their motion. For events connected by a time-like interval, deltas squared is greater than 0. The interval measures the proper time between them along an inertial path. For events connected by a space-like interval, deltas squared is less than 0. The interval measures a kind of proper distance. For events connected by a light-like interval, delta squared equals 0. The events are connected by a light ray. The departure and reunion of the twins are time-like separated. There's a well-defined proper time between them. But the proper time depends on the path through space-time. The Earth twin follows a straight path purely through time, no motion through space. The interval along this path gives maximum proper time. The travelling twin follows a bent path through space as well as time. The interval along this path gives less proper time. Both proper times are invariant along their respective world lines. All observers agree on how much each twin aged. The asymmetry is encoded in the geometry. It's not frame-dependent or observer-dependent. It's built into the structure of space-time itself. Let's also consider what happens if the twins don't reunite. Suppose the travelling twin never turns around. They just keep going, flying away from Earth forever. Is there still a twin paradox? Not quite. The paradox specifically arises when the twins reunite and compare ages. If they never reunite, they can't directly compare clocks. They can only exchange signals. And those signals will be Doppler shifted. From Earth's perspective, the travelling twins' signals arrive increasingly red-shifted and slowed down. The travelling twin appears to age slowly. From the travelling twins' perspective, Earth's signals also arrive red-shifted and slowed down. Earth appears to age slowly. In this case, the situation is symmetric. Both see the other aging slowly. There's no paradox because there's no reunion, no direct comparison, no asymmetry in the paths. The travelling twin is in a single inertial frame. The Earth twin is also in a single inertial frame. Different frames, but each is inertial. It's only when one twin accelerates to return breaking the symmetry that the paradox arises and resolves. This reinforces the key point. Acceleration is the crucial difference. Now, what about more exotic scenarios? Suppose the traveling twin approaches a black hole, orbits close to the event horizon, then returns to Earth. Near a black hole, gravitational time dilation is extreme. Time passes much slower deep in the gravitational field. The traveling twin, orbiting close to the black hole, experiences intense time dilation, both from their orbital speed and from the strong gravity. They might orbit for what feels like a few hours to them, but when they return to Earth, decades or centuries could have passed. This is the twin paradox on steroids. And it's theoretically possible. Black holes exist. If you could survive the tidal forces and navigate close to the event horizon, you'd experience extreme time dilation. From your perspective, time would pass normally. You'd feel your heartbeat, think your thoughts, experience seconds ticking by. But relative to the rest of the universe, you'd be living in slow motion. When you returned, everyone you knew would be gone. Civilizations would have risen and fallen. The universe would have aged while you barely aged at all. This is forward time travel taken to its extreme, and it's not science fiction, it's a prediction of general relativity. Of course, black holes introduce complications. The tidal forces near a black hole are immense. The difference in gravitational pull between your head and feet would tear you apart, a process charmingly called spaghettification. For stellar mass black holes, you'd be spaghettified long before reaching the event horizon. But for supermassive black holes millions or billions of times, the sun's mass, the tidal forces at the event horizon are much weaker. You could, in principle, cross the event horizon intact. Once inside, though, you couldn't return. The event horizon is a one-way boundary. All paths lead inward to the singularity. So while you could experience extreme time dilation by approaching a black hole, you couldn't orbit indefinitely and return. You'd either stay at a safe distance with moderate time dilation, or cross the horizon and be lost. Still, even moderate time dilation near a black hole is significant. Orbiting at a safe distance, say, a few times the event horizon radius could produce time dilation factors of 2 or 3 or more. You'd age half as fast as someone far from the black hole. A year for you could be 2 years for them. This is gravitational time dilation, as dramatic as the velocity time dilation in the classic twin paradox. And it's been observed indirectly in astronomical systems. Binary pulsars, pairs of neutron stars orbiting each other, experience significant gravitational time dilation. As they orbit, their gravitational waves carry away energy, causing the orbit to decay. The stars spiral closer together. The rate of orbital decay can be calculated using general relativity, accounting for gravitational time dilation, space-time curvature, and gravitational wave emission. The most famous example is the Hulse-Taylor binary pulsar, discovered in 1974. Its orbital decay matches the predictions of general relativity to extraordinary precision within a fraction of a percent. This earned Hulse and Taylor the Nobel Prize in Physics. And it's a test of relativity under extreme conditions, strong gravitational fields, high velocities, dynamical spacetime. The twin paradox, extended to gravitational contexts, passes every test. Let's also think about cosmic scales. The universe is expanding. Galaxies are moving away from each other as space itself stretches. Distant galaxies are receding from us at speeds proportional to their distance, a relationship called Hubble's law. Galaxies far enough away are receding faster than light, not because they're moving through space faster than light, but because space itself is expanding. This doesn't violate relativity. Relativity limits motion through space, not the expansion of space itself. But it does raise interesting questions about time. An observer in a distant galaxy, receding from us at relativistic speeds, experiences time differently than we do, not because of velocity through space, but because of the expansion of space between us. This is cosmological time dilation. Light from distant galaxies is redshifted by the expansion, and events in those galaxies appear to happen in slow motion from our perspective. A supernova in a distant galaxy takes longer to brighten and fade, as observed from Earth, than a nearby supernova. This effect has been measured. Distant supernovae do appear to evolve more slowly. It's not because the supernovae themselves are different, it's because their light is stretched by the expansion of the universe. And that stretching affects not just the wavelength, but also the rate at which events appear to unfold. This is time dilation on a cosmic scale. The universe itself creates differences in how time passes. There's also the question of what happens at the limit. What if the travelling twin could reach light speed? The answer: they can't. Nothing with mass can reach light speed. But we can ask, what would time dilation be like at light speed, hypothetically? The Lorentz factor gamma approaches infinity as velocity approaches light speed. Time dilation becomes infinite. Proper time along a light speed worldline would be 0. For a photon, no time passes. A photon emitted by a distant star and absorbed by your eye experiences 0 proper time, even though billions of years pass from our perspective. This is one way to understand why photons don't experience time. They travel on light-like worldlines, where the space-time interval is 0. From a photon's perspective, if such a perspective made sense, the universe is contracted to 0 length in the direction of travel, and the journey is instantaneous. Of course, photons don't have a perspective. They don't have reference frames in the usual sense. That this limiting case illustrates how time dilation extends to the extreme. The closer you get to light speed, the more dramatic the effect. At light speed, time stops entirely from the traveller's perspective. This is why nothing with mass can reach light speed. It would require infinite energy, and it would result in 0 proper time and unphysical situation for anything that ages. So the twin paradox, in all its forms, reveals deep truths about the universe. Time is not absolute. It's flexible, path-dependent, geometric. Motion affects aging. Gravity affects aging. Acceleration breaks symmetry. Different paths through space-time accumulate different amounts of proper time. Yet all of this is lawful, predictable, testable. Relativity doesn't introduce chaos. It introduces a more subtle form of order. An order where time and space are interwoven, where simultaneity is relative, where light speed is the cosmic speed limit. An order that's been confirmed in countless experiments, from atomic clocks on airplanes, to particles in accelerators, to satellites orbiting Earth. An order that underlies the technology you use daily, from GPS navigation to telecommunications. An order that makes the universe coherent even as it makes the universe strange. And there's a kind of peace in recognizing this. The universe is not obligated to match your intuition. Intuition developed for everyday speeds and everyday scales. It serves you well in daily life. But it never needed to handle speeds close to light or gravitational fields near black holes. At those extremes, intuition reaches its limits. Not because intuition is broken, but because it was never designed for those conditions. Recognizing this removes the pressure. You don't have to intuitively grasp time dilation. You just have to accept that it's real. Confirmed by measurement, woven into technology, consistent with equations. Real. And once you accept that, the strangeness becomes less threatening. It's just how things are at scales beyond everyday experience. The twin paradox is one of those things. It feels strange because you're never aware of time dilation in daily life. The microseconds of difference from walking across a room are imperceptible. So your brain treats time as universal, and for practical purposes, it is. But scale up to relativistic speeds, and the effect becomes impossible to ignore. Suddenly, the principle you could overlook becomes the dominant feature. And that can feel disorienting. Like discovering that something you thought was solid is actually mostly empty space. Which, by the way, is also true. Atoms are mostly empty space. The nucleus is tiny compared to the electron cloud. But the electromagnetic forces between atoms create the sensation of solidity. So tables feel solid even though they're mostly void. The same principle applies here. Time feels universal even though it's fundamentally flexible. Your brain bridges the gap. And for everyday purposes, that's fine. The flexibility doesn't matter at human scales. But knowing it's there deepens understanding. It reveals the underlying structure, the way things actually work beneath the seamless experience. And there's comfort in that structure. Because structure means predictability. It means the universe isn't arbitrary. Time dilation always follows the same equation. Length contraction always pairs with time dilation in just the right way to keep light speed constant. Acceleration always breaks symmetry in the same way. These aren't random coincidences. They're consequences of spacetime's geometry, and that geometry is consistent. Everywhere, always. The universe has rules. And those rules don't change depending on whether you're watching is less than #0, 5 is greater than. They just are. This is reliability at a deep level, not the reliability of familiar experience, but the reliability of fundamental law. And perhaps that's the ultimate comfort. Not that everything is simple, but that everything is lawful. Not that you can intuitively grasp every principle, but that those principles exist and can be understood. The universe is strange, but it's not chaotic. It's complex, but it's not random. And it's knowable. Not completely, there will always be deeper questions, but genuinely, in ways that make predictions, in ways that build technology, in ways that reveal structure. The twin paradox is one thread in that tapestry, but pulling on that thread reveals so much. Time's relativity, space's flexibility, causality's structure. The unification of space and time into spacetime, the equivalence of acceleration and gravity, the constancy of light speed as the foundation of causality. All from one thought experiment. A thought experiment that seemed paradoxical at first. Two twins. One stays, one travels. Both see the other moving. Yet one ages more. How can this be? The answer, as we've explored, is geometric. Space-time has a structure. That structure assigns proper time to worldlines. Straight worldlines, inertial paths, maximize proper time. Curved worldlines, accelerated paths accumulate less. The Earth twin's worldline is straight. The travelling twin's is curved. Different geometries, different proper times. No paradox, only structure. And this structure has been tested. Atomic clocks on airplanes, muons in the atmosphere, particles in accelerators, GPS satellites in orbit. Every test confirms it. Time dilation is real, measurable, precise. The predictions match observations to extraordinary accuracy. Not approximately, exactly. Within experimental error, relativity's predictions are perfect. This isn't a theory that works most of the time. It's a theory that works every time. In every domain where it's been tested. At low speeds and high speeds, in weak gravity and strong gravity, from millisecond pulsars to GPS satellites to particle colliders. Relativity holds, not because Einstein was lucky, but because he discovered something fundamental about the universe, something that was always true, something that was waiting to be understood. And understanding it changes how you see everything. When you look at the night sky, you're not just seeing stars, you're seeing the past. Light from those stars has been traveling for years, decades, sometimes millions of years. During that journey, the photons experienced zero proper time. From their perspective, the trip was instantaneous. But from your perspective, those photons have been traveling for eons. This is time's flexibility made visible. When you use GPS, you're relying on relativity. The satellites experience time differently than you do. Their motion slows their clocks. Their altitude speeds their clocks. The net effect is a few dozen microseconds per day, and those microseconds matter. Without correcting for them, navigation would fail. The twin paradox is not an abstract curiosity. It's engineering reality. When physicists accelerate particles in colliders, they're creating tiny traveling twins. Protons zipping around at 99.9999991% of light speed. From the lab's perspective, those protons live for milliseconds before decaying or being used in collisions. From the proton's perspective, if they had one only, microseconds pass. Time dilation allows them to complete millions of laps before decaying. Without time dilation, particle physics experiments wouldn't work. The particles wouldn't survive long enough. And when you consider the universe at large, time dilation is everywhere. Binary pulsars, spiraling together, experience it. Galaxies receding from us experience cosmological time dilation. Objects near black holes experience extreme gravitational time dilation. Time is not universal. It's local, personal, path-dependent. Every object in the universe is aging at its own rate, determined by its motion and its position in gravitational fields. Yet all these different rates fit together coherently. When worldlines intersect, when objects meet, they can compare clocks, and the comparison always makes sense. No contradictions, no paradoxes, just geometry. This geometric view of time is one of the great insights of the 20th century. Before Einstein, time was thought to be absolute, a universal clock ticking the same for everyone. After Einstein, time became flexible, a dimension woven together with space into a unified fabric. This shift in understanding is profound. It's not just a technical correction, it's a fundamental reimagining of reality. Space and time are not separate, they're aspects of a single entity, spacetime. And that entity has geometry, curvature, structure. Motion and gravity are not forces acting in space, they're manifestations of spacetime's geometry. This is what general relativity reveals. And the twin paradox is a window into this revelation. By looking carefully at how twins age differently, you see how space-time works. You see that straight paths are special, they maximize proper time. You see that acceleration is detectable, it curves your world line. You see that simultaneity is relative now, depends on your velocity. You see that causality is preserved, light cones protect the order of cause and effect. All of this from one thought experiment, a thought experiment that initially seemed paradoxical. But paradoxes, when examined closely, often reveal deeper truths. Is less than #0. 5# is greater than. They show where intuition breaks down. And where intuition breaks down, there's usually something interesting happening. The twin paradox breaks down the intuition that time is universal. That intuition is based on everyday experience, and for everyday experience, it's fine. You and your friends age at the same rate as far as you can tell. Clocks on walls tick in sync. Time zones are just conventions about when to call it noon. But extend the conditions, move at relativistic speeds, experience strong gravity. And suddenly, time's flexibility becomes apparent. Your friend on the spaceship ages less. The clock near the black hole ticks slower. This isn't a failure of time to behave properly. It's time behaving the way it always does. You just notice it more under extreme conditions. And this points to something important about science. Science doesn't just accumulate facts. It reveals structure. Sometimes that structure matches intuition. Sometimes it doesn't. When it doesn't, you have a choice. You can reject the science, clinging to intuition. Or you can update your intuition, expanding it to include the new structure. The second path is harder, but it's more rewarding because it lets you see the universe more clearly, not as you wish it were, but as it actually is. The twin paradox invites you down that second path. It challenges the notion that time is simple and universal, is less than #0, 5# is greater than, and it offers, in return, a richer understanding of space-time. An understanding that's been confirmed in countless experiments. An understanding that underlies modern physics. An understanding that reveals the universe to be both stranger and more lawful than you might have thought. So where does this leave us? We started with a question: how can twins age differently if motion is relative? We've seen the answer: motion is relative, but acceleration is not. One twin remains inertial, the other accelerates. Their paths through spacetime differ, and spacetime's geometry assigns different proper times to those different paths. The straight path ages more. The curved path ages less. This is not a paradox, it's a prediction. A prediction that's been tested and confirmed. A prediction that reveals time's true nature. Time is not absolute, it's relative, path-dependent, geometric. Yet despite this flexibility, the universe remains coherent. Causality is preserved, physical laws hold, observations are consistent. Different observers see different things, but their observations fit together. The Earth twin ages 22 years. The travelling twin ages 10. Both are right. Both measurements are valid in their frames. There's no contradiction because the observers are following different paths through space-time, and space-time's geometry accounts for everything. This geometry is not arbitrary. It's determined by the distribution of matter and energy. In general relativity, mass and energy curve space-time, and that curvature determines how objects move and how time passes. The Earth curves space-time around it, creating gravity. The Sun curves space-time more dramatically. Black holes curve space-time to extremes. Neutron stars create strong fields. And throughout the universe, space-time's curvature varies, creating a tapestry of gravitational fields and time dilation effects. Yet this tapestry is lawful, predictable, knowable. Einstein's equations describe how matter and energy curve space-time. And those equations have been tested extensively, from the precession of Mercury's orbit to gravitational lensing to gravitational waves. Every test confirms the predictions. The universe operates according to general relativity at all scales where it's been tested. Of course, there are limits to our knowledge. General relativity breaks down at quantum scales. It predicts singularities, points of infinite curvature inside black holes and at the Big Bang. These singularities suggest the theory is incomplete. A more fundamental theory, unifying general relativity with quantum mechanics, is needed. String theory, loop, quantum gravity, and other approaches attempt this unification. But so far, no complete theory of quantum gravity has been confirmed. This is an active area of research. The questions are deep, the answers are elusive, but the search continues. Still, within its domain classical spacetime, away from quantum extremes, general relativity is extraordinarily successful. And the twin paradox is a beautiful illustration of its core principles. Time is flexible, space is flexible. Together, they form spacetime. Motion through spacetime affects aging. Acceleration changes your path, and different paths accumulate different amounts of proper time. Simple in principle, profound in implications. By the time you look back at the question we started with, it feels different. Not because it became simpler, but because you can finally see the shape of the answer. The twin paradox isn't a paradox at all. It's a demonstration. A demonstration that time is more flexible than everyday experience suggests. That motion through space affects passage through time. That acceleration creates real, measurable differences. And that beneath all this strangeness there's structure, lawful, consistent, knowable. The universe allows twins to age differently, not as a glitch in reality, but as a consequence of spacetime's geometry. And in that geometry there's something to trust. Not that everything is simple, but that everything is lawful. Not that you can intuitively grasp every consequence, but that those consequences follow from principles that can be understood. The twin paradox resolves, not by removing the strangeness, but by showing how the strangeness fits into a larger coherence. Space and time weave together, motion bends that weave, and aging follows the path you take through it. This is the universe we live in, strange, precise, reliable, and it's the only universe where time could work the way it does. Consider what this means for existence. You are traveling through space-time right now. Your world line extends from your birth into your future. Every moment, you're moving through time at 1 second per second from your own perspective. But from another perspective, someone moving relative to you, your rate is slightly different. Not noticeably. The effect at human speeds is minuscule, but it's real. You and everyone around you are experiencing time at very nearly the same rate because you're all moving at similar speeds in similar gravitational fields. But in principle, every person is experiencing their own proper time. We're all traveling through space-time together, but each on our own world line. And those world lines accumulate proper time at their own rates. This personal time, proper time, is what you actually experience. It's measured by clocks you carry, by your biological processes, by your aging, and it's invariant. All observers agree on how much proper time has elapsed along your world line. But coordinate time, the time measured in some external reference frame, is frame-dependent. Different observers assign different coordinate times to the same events on your world line. This is why the travelling twin ages less. Their proper time, the time they actually experience, is less than the coordinate time measured by the Earth twin. Both measurements are valid, both are correct in their respective frames. But proper time is what matters for aging, for experience, for existence, and proper time depends on your path through space-time. There's a kind of poetry in this. Your path through life isn't just metaphorical, it's literal. You're tracing a world line through space-time. The choices you make, where you go, how fast you move, affect your path. And your path determines how much time you experience. In practice, the differences are negligible. Human life doesn't involve relativistic speeds or extreme gravity. But in principle, the connection is real. Your aging is a geometric property of your world line, and that world line is drawn through the fabric of space-time. This view of existence as a path through space-time is one of the gifts of relativity. It unifies time with space. It reveals the geometry underlying motion and aging. and it provides a framework for understanding phenomena that would otherwise seem paradoxical. Like the twin paradox, which, as we've seen, is not a paradox at all. Just geometry. And geometry, for all its abstraction, has a kind of solidity. It's not opinion or interpretation, it's structure. The angles of a triangle sum to 180 degrees in flat space, always. The Pythagorean theorem holds in Euclidean geometry, always. And in spacetime, worldlines accumulate proper time according to the metric, always. This is mathematical certainty applied to physical reality, and it's comforting. Not because it makes the universe simple, it doesn't, but because it makes the universe lawful. Laws don't guarantee simplicity, but they do guarantee consistency. The same laws apply everywhere, to everyone, at all times. You can't opt out of time dilation. It's not a matter of belief. If you move fast, you age slower. If you stay in a gravitational field, you age slower. This happens whether you know about it or not, whether you accept it or not. The universe doesn't care about your preferences. It just follows its laws. And that impartiality is, in its own way, reassuring. The universe is reliable. Not reliable in the sense of being comfortable or convenient, but reliable in the sense of being consistent, predictable, governed by laws that don't change. You can calculate what will happen, and it will happen. You can predict how much twins will age, and when they reunite, the prediction holds. This is the kind of reliability that science reveals. Not emotional comfort, but structural stability. The universe has a foundation, and that foundation doesn't shift. So rest in this. The universe is vast. It's ancient. It's strange beyond everyday intuition. But it's also reliable, governed by laws that hold across billions of light years and billions of years. Time dilation happens, always. And that consistency creates the structure we see, the structure that allows causality to work, the structure that keeps past, present, and future distinct, the structure that makes the universe knowable. The twin paradox reveals this structure. It shows that time is flexible within a lawful framework. That motion affects aging in predictable ways. That acceleration breaks symmetry, but in a way that's consistent and measurable. That space-time has geometry, and that geometry determines proper time. All of this is strange, but all of it is real. Tested, confirmed, applied in technology. The twin paradox is not a curiosity from theoretical physics. It's a description of how the universe actually works, and the universe works this way everywhere. Not just in thought experiments, not just in extreme conditions. Everywhere, always. Time is relative, space is relative. Together, they form space-time. And space-time is the stage on which everything happens. Every event, every motion, every interaction. The geometry of that stage determines how time passes for every observer, and that geometry is lawful, consistent, reliable. This is the delayed universe we explored before, where light travels at a finite speed, creating a delay between events and observations, where that delay isn't a limitation but a feature that preserves causality, that keeps past and present and future distinct. And now we see another feature: time's flexibility. The fact that different observers experience different amounts of time. This flexibility, too, is not a limitation. It's what allows the universe to be consistent. What allows light speed to be constant for all observers? What allows causality to be preserved even when simultaneity is relative? The universe is coherent, not because it's simple, but because its complexity follows from a small number of fundamental principles. The constancy of light speed, the equivalence of acceleration and gravity, the geometry of spacetime. From these principles, everything else follows. Time dilation, length contraction, the twin paradox, E equals mc squared, black holes, gravitational waves, all consequences of the same underlying structure. And that structure is beautiful, strange, intricate, counterintuitive, but beautiful. Beautiful because it works, because it makes predictions that are confirmed, because it reveals connections between phenomena that seem unrelated, because it shows that the universe is not arbitrary. It has rules, deep rules, rules that govern everything, and those rules can be understood, not completely, not all at once, but genuinely, enough to make sense of what you see, enough to predict what will happen, enough to trust that the universe is lawful. So, when you think about the twin paradox, don't think of it as a puzzle. Think of it as a window into the nature of space-time, a window into the flexibility of time and the constancy of physical law, a window into a universe that is both stranger and more reliable than everyday intuition suggests. And through that window, you can see something comforting. The universe is vast, it's old, it's complex, but it's not chaotic. It follows rules. And those rules, for all their strangeness, are stable. They don't change, they don't break. They just are, and you can rest in that. The twin paradox has resolved. The travelling twin ages less because their world line through space-time is curved. The Earth twin ages more because their world line is straight. Different paths, different proper times. No paradox, only geometry. And that geometry is the foundation of everything. Time, space, motion, aging. All arising from the structure of space-time. All lawful, all consistent, all knowable. This is the universe you inhabit. Number, strange, flexible, lawful, and worthy of trust. Not because it matches intuition, but because it follows principles that can be understood. Principles that reveal structure beneath the strangeness, order beneath the complexity, coherence beneath the mystery. So settle into this knowledge. Time is relative, but that relativity is lawful. Twins can age differently, but the difference is predictable. The universe is strange, but it's not arbitrary, and in that reliability, there's something to hold on to. Not as an anchor against change, the universe does change, but as a reminder that beneath the change, there's structure. Beneath the complexity, there's order. Beneath the strangeness, there's coherence. The twin paradox is no longer a paradox. It's a feature of the universe, a feature that reveals time's true nature. And that nature is both stranger and more trustworthy than you might have imagined. Strange because time bends, flexes, depends on your path. Trustworthy because those effects are lawful, predictable, consistent. This is the universe you live in. And it's been this way all along, waiting to be understood. Better sleep, a lighter day.